cubed is 1 minus u, 3u, plus 3u squared minus u cubed. The middle one is 3u minus 6u squared plus 3u cubed. The third one is u cubed, is 3u squared minus 3u cubed. The last one is u cubed. So does that help us now look and see how to separate out the u's? Well, hopefully we can pull out a u to the 0, which is 1. Pull out u's, u squared and u cubed, and get the first column of 1 minus 3, 3 minus 1, which is, when you multiply those together, you get your first Bernstein polynomial. There is no u0 in the second Bernstein polynomial. So you put a 0, 3 minus 6, 3. And you just separate it down. Okay? You see that? So I think expanded out, it looks something like that. So the two matrices on the right are numbers. The CAD system can slam those two matrices together, hold a single matrix in its memory, and then when you give it a u value, it can very quickly put that in and give you a point on the curve. Or it can very easily draw the curve by incrementing u from 0 to 1, some small step along the curve to turn on pixels on the screen. Okay. The form that you will typically see it written in the textbooks and in the literature is you'll see it as a U matrix times an M lowercase be times a P matrix. Okay, so that's the standard matrix representation, and when you see that, it's really in your mind you should be thinking of the representation just above. So what are the mapping functions going to be? Well, the mapping functions are nothing more than the x's multiplied into that to give you an equation, the y's multiplied into that to give you a second equation, the z's multiplied into it. So in effect, that matrix gives you all three mapping functions. So we're going to do a little example. Take these values, plug them into the matrix above, take a second on your calculator, or if not on your calculator, do it longhand if you don't have a calculator, and see if you can actually come up with the x mapping function as a polynomial, the y mapping function as a polynomial, the z mapping function as a polynomial. So see if you can kind of work back to the polynomial form. Simplest polynomial form for x, for y, and for z. So the first thing that I would do is I'd take these values and fill in the P matrix correctly. The second thing I would do is begin taking the row out of the M matrix, multiplying it times the first column of the P matrix, the second row, and I would just do it literally the X first. Write those down, and then multiply it times U, and that'll get you the mapping function. Is that any place close?
Yeah, that's right.
That close? Okay, we're not going to take any more time. Hopefully you did in your mind something like this. You plugged in these numbers. You expand the matrix, multiply it out. You should get something like the mapping function for x being 2 plus 6u plus 10.5 u squared minus 8.5 u cubed. Question?
Yeah, it doesn't matter the order you put the points in the matrix.
It does. And so you start with P naught, P1, P2 going down the curve. Okay?
It would have gone like that rather than like that.
Yeah.
You'd switch the rows.
Right. So you can also, you'll see in the textbooks, you'll see in the journals that occasionally the U vector is not on the left. The U vector will be on the right, and it'll be a column. And if it's a column, the points will be the first vector. The MBE will still be in the middle, but how will the MBE be written? It'll be transposed. Okay? It'll be transposed in the middle, and you'll have a column for the U vector running down the side. So it doesn't matter whether it's kind of written this way or the U is a column instead of a row. The math is just slightly different, but it still all works out. So going back to our mapping functions, the Y looks like that and the Z looks something like that. Okay. So what does a Bezier line look like? What's our U vector going to look like? 1 and U. So 1 and U. What's our MBE going to look like? It'll be a 2 by 2, right? And what is our P's going to look like? 2 P's, a P naught and a P1. So it's going to look something like this. Now if I take and multiply 1 and U times 1 and 1 minus U, what monomial do I get? I get 1 minus U. What is the other monomial that I'm looking for? U, and that's the next column. And so this is a representation of exactly what we started with on our parametric line. So our parametric line is a Bezier line. It's also a NURB line. It's also a B-spline line. It's also a Hermite line. All of them look exactly the same. What does a quadratic Bezier curve look like? Well, it looks like 1u squared. It gives us this MBE matrix that is 3 by 3. And then we have a point matrix that in this case is a 3 by 3 because we've got X, Y, and Z stacked in there. How did we get these columns of our MBE? Well, they come from Pascal's triangle, partially. So this first column is the third line on the Pascal's triangle, which is the quadratic exponents of a 1 minus u squared expansion. These are the coefficients. The third line is the expansion of 1 minus u cubed quantity cubed. Those are the coefficients. So for the first column, we can kind of pick them off, right? What is the second column? Well, it's the line just above it, because we have a term in that u, 1 minus u. That's one of our blending functions. We have 1 minus u squared. We have u, 1 minus u, and we have u squared. The coefficient right here is 2 choose 1, which happens to be 2. When we multiply that all together, we end up with this being the term, and we multiply it by 2, and we get a 2 and a minus 2. And this is the power of our u squared for our last one. What in the world is that? What order? Fourth order. So, to get all of this stuff, we just keep writing Pascal's triangle. 1, 4, 6, 4, 1. So this is the first column. How do we get the second column? Well, it's what coefficient? It's this coefficient right here times the row above it. How do we get the next one? It's this coefficient times 2 rows above it. How do we get the next one? It's this coefficient times the row just above it. And so you can very easily map out in the curve if you understand the expansion of these Bernstein polynomials and how they come from. And they come really fast out of that.
I missed how we get the signs, I guess, for those. Where the negative signs coming from if you're just looking at the...
So the negative signs is every other term.
It's always...
And it's because you have cubed and squared terms and things like that, and so you get a mixture, and it's every other one. So, good question. So I would suggest that between now and Thursday, you try and set up like a 7th order MBE. Just write it down. See if you can write it down, and if you can't write it down, expand it out. A 7th order, so this is a 4th, 5th, 6th, 7th, we want to be down here, okay? We want to be down there, and just see if you can't fill in the matrix in a few seconds. Because once you've done it, 7th order, MBE. And I think that was the end. See you on Thursday.
So each of the different curve, like the Hermite curve and stuff, they do it differently. They'll give you a different result on the curve.
They will. We'll talk a little bit about that on Thursday. So it's really that center matrix. The P never changes. The U never changes. It's what does that middle thing look like? And it's because it's not a Bernstein polynomial that's being expanded. It's a nerve polynomial, or it's a Hermite polynomial.
So about that, like the...